student to keep adding to this software. Okay, so in the past, in the beginning, I didn't write the software. I didn't want to write the software. I just want to do that, think of the ideas, and concepts, and have somebody else write the software. But at some point, you may have a student, and I have several students who wrote very good software. Okay, probably more than they need for a PhD, and then they graduate, right? And then I have an idea to improve on that software. Okay, but that student is the only one who can do it because that student owns the software, right? So I would ask a student who is now a professor himself to put this thing into the software. And after some time, this professor becomes a department head of his university, of his department. Then I have to ask this department head to fix this software so that I can add something else. And after a while, this department head becomes a dean, right? And I have actually one student who is now vice president of a university. Okay, so it becomes, I mean, hard, right? I mean, this former student has a life of his own, has a career of his own. And so, but I get stuck. I mean, unless this student does it, I can't proceed, okay? Because I don't own the software. I can't do anything myself, okay? So at some point, I decided, okay, I'm going to write my own, and then I can do anything I want to it. And that became Guide. Of course, it evolved into much more than what was in the previous version of the software. Okay. So, so the first idea here is you select xi first, then find ci only for the chosen xi. All right. So I don't, for each xi, I don't try to find what is the best ci. I find what is xi first, and suppose I find that, oh, the best xi is x5. Then I look for c5. I don't look for c1. I don't look for c2. I don't look for c500,000. Right. So that idea originally was meant to save time. Originally, when I first started thinking about this way back 1984, 33 years ago, I just wanted to have a cheap version that runs very fast. I don't expect to be better than the standard at that time, just something that's fast and cheap. And then it worked. It worked in the sense that the accuracy is not bad, and the accuracy is not bad because of pruning, really. It's pruning. Pruning is the savior. You can do things suboptimally, and the tree may not be as small as the optimal tree, right? But if you know how big the tree should be, okay, you can still get a pretty good result, right? Like your cook, right? You're not using the optimal ingredients. You're not using the freshest ingredients. You're not using the best cooking things. And so you may take a bit longer to come up with this thing. But if you have an expert taster, right, and the guy can tell you, oh, don't overcook it. This is the right time to take it out. Then it may still be good enough. So this one idea, which was motivated purely by speed, does indeed deliver on speed. So when I first thought of this idea, and then I had my first PhD student work on it, I had no clue whether it would be accurate or not. But I was darn sure it would be fast, right? You can see it's fast, right? The only thing that maybe will affect its performance is how well do you select this. Obviously, if you select this poorly, right, then this is not going to be so good, right? And so after many years of trial and error, eventually I came up with this chi-square test method, okay, which I think is pretty good. But the main thing good about the chi-square test method is it allows me to handle missing data, okay, seamlessly. But at that time, when I think about the chi-square method, I never really even thought about missing data. Now, then there's a second key idea that allowed Guide to fit all kinds of models, right? So you remember I showed you this slide before, right? regression. Now, we can fit least squares. We can fit, for least squares, we can fit weighted least squares, we can fit stepwise linear least squares, multiple least squares. And we can fit least median of squares, which is not squared error, right? We can fit quantile regression, which is not squared error, Poisson proportion hazards. So we can fit all this. We can do all this. And you know, these things are very expensive to fit, right? You see, if you try to fit just piecewise linear, so at each node, you see the CAD method will fit this with a white bar and will fit this with a white bar and a white bar, right? And then its impurity is sum of squared error. White bar. Okay? This is not difficult to calculate. I mean, it doesn't take too much time. But now, if in each node, you don't fit a constant, but you fit a linear model. All right? Then it's no longer so fast to compute, right? Because now you have to compute this. Okay? For both the left-hand side and the right-hand side, for every CI. So when you move CI, you re-estimate 2 more linear models. Okay? So you start with X1, right? You want to find the best C1. So you start C1 with here, for example, or somewhere close to that. You cannot start with here because they only have one observation, right? So you start enough so that you have some degrees of freedom to fit. So you start with something, and now you estimate all the least squares coefficients here, and the least squares coefficients, and then find the sum of squared residuals. All right? Then you move the CI a little bit, fit again. All right? Every time you move, you fit 2 linear models. Okay? Until you go all the way, and you find, oh, the best one was here, right? So the best value is here. Then you record it. The best value of C1 for X1 is here. Now you go to X2, and you do it again. Right? For X2, now you have C2. And each time you fit 2. Now that's very expensive. Now imagine Poisson regression. Right? Least squares is much faster than generalized linear models. Right? You want to fit quantile regression in here or generalized linear models. You need iterations. Right? That's why most methods based on CAD only stay at piecewise constant models. Because it's just too expensive. All right? But what does Guide do? Guide fits one model to the node T. So let's call it T, node T, right? So this is node T, and this is TL and TR. Right? It fits a model, just one model. Over here, you fit 2 models for every cut point in here. Guide fits 1 model in here because there's no cut point here, right? That's 1 model. After it fits that model, it examines the data in terms of its residuals. Okay? So, like, here, right? So you have a set of data. You have, in this example, there are 2 x's, x1, x2, right? You fit, in this case, I just fit a constant, or you can fit a plane. When you fit a plane, you have the residuals. So, and you can just cross-tabulate the residuals with each of the x variables to choose x variable. To choose x variable to split, right? And so you can see that's curvature here. I want to cut along X1, so maybe I fit 2 pieces here, because it's bending, right? Over on X2, there's no bending, so I don't want to cut it, right? So I want to identify the variable to cut, and the chi-square test does it for me. But the chi-square test is based on residuals. That means I can fit any kind of model I want, because I only fit it once. As long as I get residuals, I can proceed. Right? You see the chi-square test here, the rows are the residuals. So I can fit a quantile model, I can fit a Poisson model, I can fit any kind of model. As long as there are residuals, I can identify curvature. Right? Okay, so I fit one model, I use the residuals, okay, all right. So the moment I use residuals, I'm not locked into what model, whether it's piecewise linear, piecewise quadratic, whether it's least squares, whether it's quantile, whether it's Poisson, right? Okay, and that's why I can fit, that's why, you see, that's why you see that I can fit all these things. Because the underlying concept is the residual. Okay? So once I use the residuals, I can now choose, I can choose xi based on chi-square test of the residuals. Okay, so these are the 2 key ideas that gives guide so much mileage. All right. First of all, if you want to have a method that's very sophisticated, that's very powerful things, right? It must save time. It cannot, you would think that if I want something more elaborate, I have to pay more time, right? I have to pay more. So like you have a cell phone, you want the next model, you pay more because the next model has more features, right? So every time you go up, you want more features, you want to pay more. But the card method already is paying a lot. So it's already not very fast, okay? So you want to be something with more sophisticated, much more powerful. You have to somehow find this savings somewhere, right? And this step saves me a whole lot. Because it saves me a whole lot, I can fit more elaborate models, right? But that's not alone, that's not enough. I'm fitting a model only one time. Here, this method, you fit 2 models for every cut, for every variable. Right? Of course, after I pick the xi, I still have to do a sweep on that xi, right? And then for each cut, I still have to fit 2 models, okay? Right? Okay. But this is sort of like another shortcut that enables all these fancy things that come after that. All right. So let me go back to this subgroup thing. So we were talking about this breast cancer data, right? And we saw that the treatment was, on average, quite effective. The treatment is significant, even after you control for all these variables. But if you just look at this regression coefficients, you can tell what is a subgroup. You can just see that the treatment is significant, right? After you adjust for all the covariates, but it doesn't tell you who are the people who will not benefit from the treatment. To do that, you use something like guide, and now guide finds you a X variable, which is progesterone receptor status. It finds you the cut point, which is 21. Some people, when I show this to them, they thought I choose the cut point 21. No, I don't choose. I don't even know what is progesterone receptor status. Okay, so 21 is one of the C values. Okay, it sweeps through, right? And it finds that at 21 there's not much effect here, and there is a big effect there. All right. Guide actually has another method, which is called the GS method. So this one is called GI. G stands for guide. I stands for interaction. S here stands for sum of chi-squares, because everything is based on chi-squares. So if you use the other option in guide, you get this second tree, all right? And it splits on number of positive lymph nodes. Okay, number of positive lymph nodes is an indicator of how much the cancer has spread in the body. All right, the larger number of positive lymph nodes, the more the cancer has spread. So this says if you have 3 or fewer positive lymph nodes, then the survival prospects look like that. The treatment is still effective. If you have more than 3, then it's like that. So you look at these two, the treatment helps in both cases. But in this case, people die faster, right? That's because the cancer has spread. Okay. So this is a prognostic variable. So P nodes is a prognostic variable, right? If you know that your cancer has spread a lot already, the doctor will say, well, I'm not so confident, right? Compared to a patient whose cancer is only just beginning. So with this option, you can identify prognostic variables. With this option, you identify predictive variables. So the term is called predictive. Predictive are variables that interact with the treatment. Incidentally, okay, no, this is not this example. All right. So how does guide find these trees? All right. So there are a few key ideas. The first key idea is to use a piecewise linear model. Right. So I first started working on this problem maybe 8 years ago. There's a statistician from a drug company, and he was interested in this problem called subgroup identification. I never heard of subgroup identification. So what happened was that about 8 years ago, the University of Wisconsin started a collaboration with this drug company, and to get some student support, graduate student support. So the drug company agreed to give some summer internships to our graduate students. And these students do not have to spend time at the company. They do the work, in Wisconsin, and they're paid maybe $5,000, right, to do some simulations or whatever that people in this drug company are interested in doing, right? So it's a small problem, mostly sort of more like a donation to the university, right? And then in return, but the company wanted each student to be supervised by a professor. So I had a student, and they actually there was a problem that was given to the department, and the problem was the following: have a student write a computer program that will do a million by million principal component analysis on a laptop in 1 hour. Okay, a million by million variables, PCA. Can the student, so give you $5,000, can you write a computer program that will do a PCA, principal component analysis, right, on the laptop that will run in 1 hour? Okay, so that problem was actually given to one of my colleagues who accepted it, but after a few days he realized that it's too hard. Okay, so he turned it down, together with his students. So the department chair asked me, hey, there's this free project, gives your student $5,000 and they give me $1,000. So they give the faculty advisor $1,000 and the student $5,000 to solve this problem. And so I said, oh, good, okay, I can do it. I think my student can do it. I have no clue. Actually, I had no clue. So after I was told what the problem is, I started to think about it, and then I thought conceptually PCA is solved, right? PCA mathematically is solved, but computationally, it's a different story, right? Then I started looking around, Googling, I found that, gee, it's hard. And then I asked one of my sons, who is in computational biology, And he said something like, well, if you can do it, you'll win the Nobel Prize or something, I mean, okay, if you can do it. And I went back to this company statistician. I told him that I think you need parallel processors. He said, I know, we know. He said he knows. They have parallel processors in the company. He just thought it was just something for a student to do. Okay. So we agreed it's impossible. Then I asked him, what are you really trying to do? Okay. So he said he was trying to look for these subgroups. Okay. He was trying to look at subgroups, but he was worried about interactions. Subgroups defined by interactions between covariate variables, right? Subgroups not just defined in terms of linearly, but maybe in terms of xi times xj. So, and then the other question I asked him is, do you ever collect 1 million variables? I mean, that seems like a lot of time to collect data, right? There's a lot of data to collect, 1 million observations. I mean, 1 million variables per subject. He said, oh, no, we typically maybe 1,000 variables we collect. So his K is 1,000. But he was worried about interactions, so he derived cross products. Now, what is 1,000 choose 2? That's how many cross products, right? What is 1,000 choose 2? 1,000 choose 2 is 500,000, right? So the cross product is already 500,000. So it's very easy to reach 1 million. So that's how he got 1 million. He started with 1,000. Well, you can even go beyond 1 million, right? Take 3-factor interactions. Right? So you don't really have to collect those. You just tell the computer to calculate. And you can get a lot of variables. Right? And they're doing this not because they're silly. They worry about ignoring interactions. Right? So they put in interactions. Once you put in interactions, you have this huge matrix. And then I asked him, what are you really trying to do with this PCA? And then he told me this. And then I said, well, have you tried have you tried regression tree? The only thing I know how to do is regression trees. So if we can turn it into a regression tree problem, maybe we can solve it. And he said he has already tried it, and it doesn't work. The reason is following. Most of these people, when they use regression trees, if they've not heard of guide, they use CART. Right? You use CART. Now your predicted variables are 1 million. Or even if you don't have interaction terms, just 1,000, right? You have a treatment variable, hormone therapy or not, right? You put that into the CART model, what happens? It becomes a regular predictor. What does a regular predictor do? It splits the data. You throw it in, at some point it will say, all the placebo go to the left, all the hormone, those who received hormone therapy go to the right. They're separated. What you want is you want to keep them together so you can estimate the treatment effect, put them together in a model, right? So that's why, I mean, he wasn't wrong. I mean, you use CART. CART fits a piecewise constant model, right? You have gene expression 1, gene expression 2, and so forth. And then you have treatment, yes or no, right? You put in a model, this yes or no variable is treated same as gender, yes, male or female, same as gene expression, and it's either picked up to split a node or not picked up. If it's not picked up, there's no more treatment in the model, right? If it's picked up to split, then you separate the placebo from the patient, the treated. You may as well separate them, analyze them from the start separately, right? So I was convinced for a year or more that, yeah, you cannot use regression trees. And then we tried something that he thought of, and we spent a whole year trying to, but we only got epsilon improvement to his method, right? Which turns out to be not very good. And then one day, I realized this idea, okay? You see, the CART method, if you use CART, it will fit a constant in each node. It will fit this model. In each node. So that's why the beta 0 hat is Y bar. That's the mean, right? And that's because CART can't do anything else. But you need to fit this model. All right? So what you need is, instead of that model, you should fit this model. Say, let's call this beta 1, beta 1, if, so Z is my treatment variable, right? So this is one treatment. Beta 2, if Z equals to 2, beta, say, D, if Z equals to D, right? So in our example, we only have hormone therapy or no hormone therapy. So Z equals 1 may be no hormone therapy. Z equal 2 is hormone therapy. Right? So this model can be written as that model, right? Equals to Z K not equal to 1, something like that. Beta. Right? So you set one level to be baseline. So beta 0 is actually beta 1. Right? So this model can be expressed like that. So basically, in each node, you want to fit a Y bar for each treatment. Not just a Y bar for everybody, regardless of what treatment they get. Okay? So you want to fit a Y bar for each treatment. So this is a linear model. And that now, if you fit that linear model, you can estimate the beta k's, which are the treatment effects, which is what you want to do, right? You want to estimate the effect of treatment versus placebo, right? And then I said, it's already in Guide. Guide can fit linear models. This is a very simple linear model. You know, Guide can fit linear models like this. Right? That's absolute. Okay? So now my XKs are just my indicators. Just my indicators. So the software really can handle this generally. Right? So it's just, I don't have to do anything with the software. You can do it right, you can apply it right away. So that was the first idea that you know, I thought of. I didn't think of this idea because I just thought, well, CART wouldn't do it. But then, well, this is not CART, right? And then, so once we have this model, we have residuals, and we do the chi-square test. So this is what basically Guide would do, right? Once you fit this model, you get the residuals, you do a chi-square test, and you can choose the variable to split the node. There's another method called MOB, which stands for model-based trees. It's in a package called Party, P-A-R-T-Y, and there are two functions there, C3, which is conditional inference tree, and MOB. They try to do the similar thing to what Guide does. Guide uses chi-square tests, right? And uses the chi-square approximation to the Pearson chi-square statistic. They do permutation tests, which is okay, but you can imagine how much more time you spend deriving the permutation distribution, right? So they do that, and also they can handle missing values because they just decided they don't handle missing. But if you use the Guide chi-square test, you have a column for missing values, and that's okay, right? All right. So this is an example of how Guide can find the right variable, right? So this is an example. Suppose my true model is this. So I have x1, x2, and so forth. Suppose only x1 is the important variable, right? And suppose the data are generated this way. So there's a baseline, beta 0, and this is z equals 1, think of it as a treatment, and z equals 0 as placebo, right? And let's suppose that the larger value of y is better, right? So if a patient is given the treatment, think of y as survival time, then survival time is increased by 0.2, say 0.2 months, right? If the patient is not given the treatment, then Z is 0, this will drop out. Okay? And then now, depends on what is the value of X1. Okay, so X1 may be some biomarker. In this case, if the biomarker is positive, so biomarker is positive, right? The survival time is lower. Okay, so think of X1 as age, right? You're older, your survival time will drop. If you're younger, your survival time will increase, right? So that's the variable, the age variable effect. Then now I have an interaction. Okay, this interaction says that your survival time is increased by 3.6 if you're older and you're given a treatment. Otherwise, you don't have any increase. Okay? So if you're an older person, so this drug maybe is very good for older people, right? If you're older, maybe it doesn't apply to kids. So maybe this is some type of cancer, that if a kid has that cancer, this drug doesn't work very well for the kid, right? So that's the true model. We don't know what is true model, right? Look at the data. So we only see the data. The data looks like that, right? I put in red the people who are given the drug. And the people who are not given a drug, I put in blue. Okay? So immediately you see there's something going on here, isn't it? At 0. There's something going on here. When X is negative, they're all mixed up, right? The treatment doesn't do any much good. The blue and red are together. But once X is positive, then the drug does a miraculous amount. And if you don't give a drug, people get worse, right? So this is the subgroup, right? X bigger than 0 is a subgroup. Okay? Now, if you look at this, you can say, oh, yeah, that's a subgroup, right? But suppose now you have 500,000 X variables. You have to look at 500,000, 500,000 of such pictures. There's a lot to look at, right? If you only have 10 variables, you can look at 10 pictures. Maybe it's okay, right? But if you have a lot of variables, you look at so many of these pictures. That's very tedious. Computers can check these pictures much easier. But as I said many times, computers have no eyes. So computers can print this picture very well for us to see, but the computer cannot see it themselves, right? So if there's X2 that is totally independent of the response, right? Then you see basically they're all like that. Right? If you plot it against X2, X3, they're all like that. Right? You don't see the pattern. So now how do we tell guide that here's a pattern? Well, we fit this to the data, which is like this. What does it mean when you fit this to the data? What are the residuals? If you fit this to the data, it means you separately fit a constant to the blue points and a constant to the red points. That's what it means, right? When you fit this model, you're fitting two means, one for the treatment mean and one for the placebo mean, right? So if you fit this model to the data, you will, for the red data, your mean will be somewhere like that, right? Okay? And then your residuals will be like that. Agreed? You see, you fit a mean to the red points. This part will all have positive residuals, and this part will all have negative residuals, right? You fit a mean to the blue points, you see that this part will give you positive residuals, and this part will give you negative residuals, right? Right? Now, if you're not colorblind, you see a pattern, right? If you're colorblind, well, you may still see a pattern if you're smart enough to see that these are crosses and these are circles. But if I plot all of them as circles, I just have two different colors. If you're colorblind, you will see no pattern, right? Well, the computer is colorblind. Computer is not only colorblind, computer is blind, showing that colors no use. But what I can tell the computer to do is look at just the blue points separately. Here. So this is my original data. Okay, so I just replotted this picture and this picture. Okay, I just replot these two pictures and put them up there. Right. Now I extract from here the blue points, extract from here the red points, and then now I do my chi-square test on the blue points and chi-square test on my red points, and then I get very significant chi-squares. If I do this with x2 or x3, I will not get significant. There will be a lot of overlap, right? If x2 is independent of the data, the response, they will not have this separation, right? So even if I plot the red points or the red points or blue points, they will get just noise, just random, right? And my chi-square will be small. Okay? So what I do here, what Guide did is actually exactly do this, right? Take the data, plot it against each variable in turn, fit a model, fit a constant to the red, and fit a constant to the blue. For each color, cut this into 4 regions, 4 cells, positive or negative residuals, and calculate the chi-square. Except now I have 2 chi-squares. I want to compare, I want to choose a variable, x. Previously, I only have 1 chi-square for each x. Now I have 2 chi-squares. What do? I tried adding them up. I tried multiplying them up. I tried taking the maximum of the 2. It turns out that adding them is as good as anything else. So I take these 2 chi-squares and add them up. That's why it's called a GS for sum. All right? The sum. So this basically, I take the chi-square for z equals 0 points, the points 0 equals 0. Take the chi-square for those with z equals 1 and add them up. And now I'm not limited to more than 2 treatment arms. Here we're comparing treatment versus placebo. I can compare 3. I can compare placebo versus one type of hormone therapy, another type of hormone therapy. I'm not limited to how many treatments I have. If I have more treatments, I have more colors. If I have 3 types of treatments, I have 3 tables in the end. I just sum them up. Okay? So this is the method that I use to get this picture. All right? And it detected there's something going on. There's some shift. Okay? All right. Okay, well, I already addressed this previously. Why do I cut them at the mean here? Some people will say you're losing information by grouping them with the means, but then what I can do is I can add another column for missing data, right? If I have say, so for example, in this data set, suppose X is age, X1 is age, and have some patients for whom I know which drug this patient took, and know what was the survival time, but I don't know that person's age. Somehow the age was not recorded. Right? In that case, I just have another column for each table, the 3rd column here and 3rd column here, where age is missing. Okay? Right? Or some genetic gene expression value is missing. Yeah. Okay, so that's why grouping is not necessarily totally bad, right? You can handle missing data. This is quite an important step because any other method will run into trouble. If you throw away the missing values, you can run into trouble. You impute the missing values, you can run into trouble. Okay, so this is a summary of the algorithm, right? You obtain you fit this model to the data in each node. You obtain the residuals, and then for each color, right? For each treatment arm, you do a cross-tabulation, do a chi-square test, add one more column for missing values, if there are missing values in that X variable. Compute a chi-square statistic for each table, and then convert it to a 1 degree of freedom chi-square to adjust for unequal degrees of freedom. Because this thing, you see, this thing I told you, I cut into 2 columns. I cannot always cut into 2 columns because X1 may be race. Here my X1 is continuous, age, right? Or BMI or weight. But X1 could be race. Then my column will be different races. And then my chi-square will have different degrees of freedom, right? So in order to compare them, I need to put them on a similar footing. And so I need to convert them to a single chi-square. And then I sum them up. And the rest is basically the same as what we've been doing. right? So the key idea is this picture, right? You see over here, this variable has some effect on the response, right? But only when x is positive. I want to capture this really, right? I want to capture this fact from the data. Okay? And I'm doing this in a very rudimentary fashion, right? Not only rudimentary, I'm doing it in a very computationally fast method way, because I don't want to spend too much time trying to evaluate how strong is x1 versus x2 and so forth. I mean, because I'm doing this, recursively in the whole tree, right? So I want to do this as fast as possible. Okay, here's a problem. The GS method doesn't always work. Okay, so here's another example. What do you see in this picture? What you see in this picture is that the treatment is always better than the placebo. Suppose y, large values of y is good, right? So you see that the rates are always above the blue, right? But at 0, both the red and blues are increased, are higher, right? Once x is positive, both are higher, right? So for this problem, you cannot, the method will identify this x1 variable, but it's not predictive. Predictive means that if this variable takes some values, the benefit is extra big or extra small. But here the benefit is always the same, right? So the benefit of the treatment here, the red, is always higher than the blue by, say, 1 unit or so on average, right? Except that when x1 is positive, both y's are higher, but the difference is still constant. Still constant. So the treatment doesn't do anything, really. I mean, you can give it to everybody, and it will be best. You don't have, you see, for subgroup, it's like this treatment should be only given to a certain group of people, right? Because they get maximum benefit. For this picture, give it to everybody, right? Whatever you are, if you are here, you take a treatment, you go up there. If you're here, take the treatment, go up there, right? So the treatment here is always good. There's no subgroup. It's not like this one. You see, this one, right? For this one, if your x1 is negative, doesn't matter. Nothing helps. When x is positive, then give it the treatment. Because if you don't give the treatment, these people will be worse. Right? Okay. So this for this data set, you have a problem. You will identify x1, but x1 shouldn't be identified. I mean, you can identify x1 as being beneficial, but not like it boosts up the treatment. It doesn't boost up the treatment. Okay. So I had to come up with another method, and that is the fourth idea. What you see in here is there's no interaction between treatment and x. Right? What you see in here is there's an interaction. Interaction means when x is low, the effect of treatment is one type. When x is high, the effect of treatment is a different type. That's an interaction. Right? But if the effect of treatment is constant, regardless of whether x is high or low, like here, the effect of treatment is constant. Then it, x doesn't really interact with the treatment. X just has a main effect, that's all. Okay? So to not catch these kind of things, now you really have to now put in a different model. So instead of this model, where I only include the treatment effect, I include a cross product. Actually, this is not what I do. This is what other people do. Okay? So when you want to look for interactions, they put an interaction term. Okay? And so it makes a lot of sense, right? But there are two problems. One is the cross product does not account for all kinds of interactions. Right? If you have a model that says y is beta 0, and then there's an x1, and there's an x2. If you throw in x1 times x2 interaction, yes, that's an interaction. But x1 squared times x2 is also an interaction. x1 times x2 cubed is also an interaction. But most people just include 1, x1 times x2, right? So x1 times x2 is one form of interaction, but it doesn't cover everything. That's one problem, right? This is like x1. Think of this as I as x1 and x as x2. This is like cross product, right? So this thing does not represent all kinds of interactions. Secondly, what happens if you have missing values? Right? What happens when you have missing values in this model? You cannot forget about missing values. Like if you live in Singapore, my wife always carries an umbrella because there will always be rain. Rain is a missing value. Okay? If you live in a country where there's always rain, you always carry an umbrella because you never know when the rain comes. So data, you have to worry about missing values. Right? In real data, missing values are as common as rain. If you use interactions like this, what are you going to do when some of the x's are missing values? Throw away. Right? So this is a very obvious thing. A lot of people do this, but it doesn't cover every situation. So instead, guide does this. Okay. So first of all, okay, let me remind you about linear regression. So suppose we have a linear regression like that. Suppose we have points like that. Okay? You want to fit linear regression. Can you do a goodness of fit test on this straight line? Suppose you don't know whether this straight line is the right model. Can you do a goodness of fit for the straight line? You cannot. Right? You can fit the straight line, but you cannot test whether the straight line is the right model. Some people try to do that by fitting a quadratic to compare against the straight line and see whether the quadratic term is significant or not. Right? So suppose my data is like that. Right? You fit a straight line. Okay? To see that this is no good, you can fit a quadratic and compare the sum of squares for the two. Right? You find the sum of squares for the quadratic is much smaller than the sum of squares for the straight line. Right? So you can say that, okay, I can test h naught that y equals to beta 0 plus beta 1 x plus epsilon versus h1. Right? You can do that. But this is not a goodness of fit test. Because if you do this, and if my data are like this, you will miss it. Right? If my true data are like that, you fit a straight line, and you want to test whether this straight line is good by comparing against quadratic, you conclude the straight line is good. But the straight line is wrong. It's a cubic. Right? Right? How can you do a real goodness of fit test? How can you do a real goodness of fit test that you can test this model against any other model? There's only one way you can do it. It requires you to change your design. If I have data like that, okay, and I will fit a straight line, Now I can test whether my straight line is good or not, regardless of what the alternative hypothesis is. Because when I fit a straight line, I can estimate the epsilon term. I can estimate sigma 1 hat squared, right, to be 1 over n minus 2 summation yi minus yi hat squared, where yi hat is a straight line. There's one estimate of sigma squared. So my model is this. Right? I want to test whether fx is a straight line versus not a straight line. This sigma squared is the variance of epsilon, right? So I estimate sigma squared using a straight line. And then I estimate it separately without assuming a straight line. Because this is a replicate, I can estimate sigma squared from here. I can estimate sigma squared from here. Right? So I can estimate sigma, so I call this 1 sigma squared. 2. Now I have another estimate of sigma squared. I compare the two. If the two are close, then my straight line is pretty good. If the two are not close, then my straight line is bad. So here is a simple example. So suppose my true curve is like this. Right? I don't know. Okay? I take some data, I get 2 points here. I can take more than 2. So suppose my sigma squared is very small. Right? So now my sigma 2 squared is very small because it's very little variance. But I don't know, I fit a straight line. Okay? So now here are my residuals. You see my residuals are very big in some places. Now my sigma 1 hat squared, if I use a straight line, will be big. And now they're not comparable. Right? So this is a goodness of fit test. The only way you can do a goodness of fit test if you have replicate observations. Because the moment you have replicate observations, you can estimate the sigma squared independently of the line. Right? Okay? And then you compare the two estimates of sigma squared. One independent of the line. I just use the replicates estimate. Right? The other one, I fit the line, use the residuals estimate. Okay? If the line is correct, so if this is the true line, and I get data like that. Right? Then, when I fit a line, it's almost going to be the black line. The black line is the truth, right? But if I fit it with the data, it will almost be the black line, right? Then my residuals will be the same size as if I just use the data at each design point, right? So for this kind of data, I'll find that the two estimates sigma squared are pretty close. That's actually an F test to do that, right? So basically based on the F test, right? So this is what I do basically. This is for categorical variables, but let's say with ordinal variables. Okay, so I do a test of fit. But in order to do a test of fit, I need to group them together. So roughly, this is what I'm doing. What I do. So this is a rather rough method. So I have data like that. But I do not necessarily have replicates. So just schematically, it's something like, now I treat these two as coming from the same shared x value. Okay, so I move this and move this so that they are on the same, roughly on the same line. So now I move this. Now I sort of create some replicate. Okay, create some replicate. You see, in order to do this properly, you need real replicates. You need points at the same x. Okay. But I don't normally have. So I group them. So now I have one group here, and and I treat the variation, the vertical variation between these 2 points within this group as my sigma 2. I think neighboring points to sort of be roughly close enough to each other. Okay, so this is what basically I do. I categorize in 2 groups. Here I categorize into 4 groups, but I categorize this into 2 groups. So I do it even more crude. You may be scared. What I do is sort of like, some of these hawker stalls, when you see what they do behind, you get scared. You do not eat the food, but as long as they cook it well enough, it's okay. So I may have data like that. So I treat this as one group. I treat this as another group. And I pretend that my data actually looks like this. So I have 1, 2, 3, 4, 5, 6 points. I assume that they're like that. Right? So this value may be, say, x01, and this value may be some average value. Okay? Let's call it x bar for this group, and this x double bar. Right? And I plot this at x bar, and then this points over here. 1, 2, 3. This x double bar. Okay. All right. So just to be able to get 2 estimates of the variance, one from this grouping and one without the grouping and fit a line. Why do I cut them into 2 groups? You may ask. Why do I cut it into more groups? One of the interesting things about regression trees, different from a lot of statistical methods. In a lot of statistical methods, you hear about sample size go to infinity, right? In regression trees, the sample size go to 0 because you split. Right? No matter how much data you have at the beginning, eventually you have very little observations. So if I cut this into more than 2 groups, I may not have data in any group. So that's a part of the reason. If it's categorical, then they already are a group, so there's not a problem. I add a group of missing values, and then I test this additive model. Right? This additive model is like a straight line. Okay, it's like a straight line. But once I group it, I have a mean for each group, so it's like a full model, the complete model. Right? So I test a full model versus the additive model, and then so it's standard, traditional statistical test, and then I choose the variable that is most significant. Okay, so that's what gave this result here. This result here, right? Although I should say, so far what I've told you doesn't apply to this example, because so far I've been plotting y as if they are uncensored. Here we have censored data. Right? So far I've been fitting least squares models, but here I'm fitting Cox proportional hazards model. Each node has a Cox proportional hazards model, like this kind of model, right? So how do I jump from least squares to Cox proportional hazards models? Well, it turns out that there is a very old fact. There's a very old trick. I don't know whether you're aware of it. I wasn't aware until I needed this. So after I figured this out, then I thought, oh, now I have to do Cox proportional hazards models. Now everything here is based on residuals, right? At least for the GS method. How do you define residuals for proportional hazards models? Do you guys remember? What are residuals when you have censored data? When you have survival analysis, right? Some people come up with some sort of residuals. Some people call martingale residuals, and so forth. But these residuals have exponential distributions. They are non-negative. Martingale residuals follow some sort of exponential distribution, right? And they're very hard to calculate. And I'm stuck. I depend on positive and negative residuals for my chi-square tables, and now I have residuals that are all positive. Right? And what do I do? Well, then I found out this thing. It turns out that if you look at the Poisson regression, okay? You look at the Poisson likelihood for Poisson regression, right? So that you have a Poisson density function in the Poisson likelihood. And then you look at the Cox proportional hazards model. The two are very similar. So similar that you can estimate the Cox proportional hazards model, the beta coefficients, by using Poisson regression. So if you have a routine that can estimate the regression coefficients in Poisson regression, you can use the same routine to estimate the coefficients in the proportional hazards model. That's fantastic. Because by the time I found this, I already have Poisson regression in my software. I had put it in there years ago just because I could do it. So, so how to use Poisson regression to fit a Cox proportional hazards model? First of all, the Poisson regression y is an integer, right? Non-negative integer, the y. Poisson count, right? It's an integer. In censored data, I have survival time. It's not a count. So how do you use Poisson regression to analyze this kind of data? Well, it turns out that in censored data, there is actually a non-negative integer, a 0, 1 integer, which is the event indicator. In other words, if you have a patient, so a clinical trial lasts for 3 years. If a patient dies during the 3 years, then the survival time is actual survival time. But you not only know that, you also know the patient died. So when the patient died, you say that indicator is 1. Another patient is still alive after 3 years. So all you know is this patient lived 3 years. But you also know this patient is still alive. So your indicator is 0. It is 1 if the patient died within the time. It is 0 if the patient is still alive. Turns out that is the Poisson y. It's non-negative integer, 0 and 1, although it never takes value 2. So it's not really Poisson, right? But the computer doesn't know. In some sense, computers are quite stupid, right? As long as it's not negative, it will work. So this is this is in the literature. This is not something I discovered, right? So UI is the actual survival time. We don't observe it if the person is censored, but we know the censoring time. These are censoring times, right? So you can think of censoring time as 3 years. So there's fixed censoring, right? What we observe is a minimum of 2, right? Minimum of the actual survival time and 3 years. So we have Y. And we have this indicator, whether a person died before the end of the trial, right? So this is 0, 1, okay? And if you fit a proportional hazards model, there is something called a baseline cumulative hazard function, right? So what you do is you can estimate the coefficients of the proportional hazard model by iteratively fitting a Poisson regression model with delta I, because delta I is a non-negative integer, as the Poisson response, and then take the log of this baseline cumulative hazard function as an offset. In Poisson regression, the offset is the following. Offset is like a predictor variable, except that you don't estimate its coefficient. So suppose Y is the number of, say, flu cases, right? Say in Malaysia. Okay? And say X is, say, some covariant. Right, maybe month of the year or wet month, dry month, and then Z is a state population. So it's the number of flu cases in each state, right? In each state in Malaysia or Indonesia, whatever. Okay, so Zi is a state population. Right? So Y is a count. Right? So normally in Poisson regression, you fit this. Right? But so mu now is the mean of Y. Okay? But we know that big states have more flu cases than small states. Right? So you really want to estimate the rate per capita number of flu cases, not actual number of flu cases. Right? So in the United States, Texas is a big state. So of course there will be many counts. Wisconsin is a small state. Right? So, but the rate in Wisconsin may be higher than the rate in Texas if you adjust for population. Right? So what you really want to do is you want to estimate log mu over Z in terms of its covariance, whatever covariance. Right? Okay. But if you do this, then you get log mu minus log Z equals to beta 0 plus beta 1x. So log mu equals to beta 0 plus beta 1x plus log Z. All right? So what you do is you take the log of Z to be another x variable, but you don't put a beta in front. If you put a beta in front, then this is like x1, this becomes x2. But you don't want to put a beta in front. You want the coefficient to be 1 because so you can divide back into a rate. You understand what I'm saying here? Right? I mean, you compare with this one. I mean, you can fit both models. Right? But the interpretation is different. Because if beta 2 is not minus 1, or no, it's not 1, then you move it back, you cannot get it like that. Right? So there may be some situations where you actually want to do this. Other situations where you actually want to do this. Right? When you want to do this, there's a name for this variable. It's called offset. This is a special name. It's called offset. Right? So when you run Poisson regression, whether you use SAS or R or SPSS or Stata, right? That would be an option. Which variable you want to specify as offset. If you specify as offset, it will not try to estimate a coefficient. It will force that coefficient to be 1. And it turns out that for the Cox model, this is exactly what is needed. So you take this thing and set it as an offset. Okay? But of course, this thing needs to be estimated from the beginning, so the whole thing is iterative. So you start with some initial estimate, which is the Kaplan-Meier estimate of the cumulative hazard. Then you estimate all the coefficients, and then after you get coefficients, you update, and so forth. Right? So I mean, I know this is too skimpy for you to know, but this is basically how Guide accomplishes the job, which I believe, I suspect maybe even R, even in any of this software, they probably use the same trick, because why have two algorithms? They're essentially the same. If you can write a solid Poisson regression algorithm, right, then just use this. Yeah. Okay, so I'm going to talk about some of the previous methods, but we are about time to have a break. Okay, so maybe we can take a break. I know I realized yesterday after the class, I cheated you of 15 minutes. I convinced you to shorten your break by 15 minutes so that we can go home 15 minutes earlier, and yet I went all the way to 5 o'clock. Okay, so some of you may be very disappointed that I cheated you. So, okay, so all right, we can still have 15 minutes, but we'll finish at 4:45. Okay? Unless people want me to give you back 15 minutes, then I have to stop at 4:30. But okay, we'll start at 4:45. So we have 15 minutes of break. Come back at 3:30.